So this was the problem that we were discussing in the previous class. You can see this one here. Design a two-way slab to suit the following data. Dimensions are 5 meter by 4 meter inside dimensions. Boundary conditions, all four edges are discontinuous with corners held down. It means it is a restrained slab. Live load is given, floor finish is given, material grades are given. Okay. Now you can see this one here. It is a two-way slab with corners restrained. Restrained two-way slab. There is one more case, that is unrestrained. So we are going to start with restrained slabs. Now here, step number 1 was decide the type of slab, whether it is one way or two way. Ly by Lx is 5 by 4. You look at the inside dimensions. Smaller dimension is taken along x-axis. Bigger one is taken along y-axis. So 5 by 4. So 5 by 4 is 1.25, which is less than 2. So it is going to be designed as a two-way slab. You fix up the depth. Start with your trial depth. In case of two-way slab, the span by depth ratio is between 25 to 35. I have selected say 28. As I told you, anything is okay in this range. So span by depth is 28 is taken as a trial. So 4000, smaller dimension out of 5 by 4, 4 is less, smaller one. So 4000 by D is equal to 28. From this, D is 142.8. It is rounded off to 145 here. So I am having small d 145, capital D 170. So this has already been discussed. Once the thickness is done, go for load calculations. Load per 1 meter square, 1 meter by 1 meter slab is taken. For 1 meter by 1 meter, how much is the dead load, how much is the live load, and floor finish, that you have to calculate. So floor finish is already given per meter square. Even if you multiply 1 into 1, it is going to remain the same, but it is already there in 1 meter by 1 meter format. Dead load, you can say, dead load of the slab. You should not find the dead load of 5 by 4 meter, 1 meter by 1 meter you should calculate, because it is load per square meter. So dead load is capital D. Overall depth into, that means volume into density, 0.17 into 1 into 1. 1 by 1 is planned dimension of the slab. Thickness is 170 mm. 25 is kilonewtons. That is density. So 4.25 is the dead load. Imposed load is given in the problem as 4. Floor finish is given in the problem as 0.6. If not given, usually it is taken as 1. Floor finish is taken as 1 if it is not given. So total is 8.85. Multiply by 1.5 to get factored load 13.3. Now step 2 is effective span, factored bending moment, and MU limit. So effective span is the smaller of center to center distance bearings. You can see this, it is 4.3. Because 0.3 by 2 this side, 0.3 by 2 this side, it is 4.3. Or clear span plus effective depth. Clear span is 4 meter, 0.145 small d. So 4.145. So 4.145 is smaller than 4.3. So LEX, effective span along X direction, is 4.145. Along Y direction, it is 5.145. Okay, X and Y direction is calculated. Factored bending moment along the short span, that is MUX, is alpha X into WULX square. That is effective span square. Factored bending moment along long span is alpha Y into WLX square. Only change is alpha X and alpha Y. The remaining two terms are same. WU into LEX square. When you calculate MUX, when you calculate MUY, this term remains same. WU into LEX square. It means span is same whether you calculate MUX or MUY. Okay, span should not be different. Same span. In that way only alpha x and alpha y are adjusted. In the calculation, alpha x and alpha y are adjusted in such a way that span in both the cases remains short span as per IS code method. As corners are held down, since it is a restrained slab, table 26 has to be used on page number 91. So alpha x and alpha y are calculated. I already explained this one. How do you find alpha x? For example, I'm trying to find out MUX using alpha x WU into LEX square. Here alpha x has to be calculated. You have to go to table 26. In table 26, first Ly by Lx is 1.25. Case 9 is the read the different cases in that table. This was done, I think, already. Even then, let us see where it is. I have to check now. This table, once again, I'll repeat it. This is table 26. My objective is to find out alpha x from this table. Alpha x from this table. Okay, observe this. So alpha x is 1.25, 5 by 4. Hello? What tell me? Please call me after half an hour. I'm engaging a class online. Now you can see this one here. Here you are having a 1.25 is the value. Ly by Lx is 1.25, and if you see in this table, this red color is there. No, these are Ly by Lx ratios. You can see this at the extreme end. Ly by Lx means this whatever 1, 1.1, 1.2, these are all Ly by Lx ratios. You will find that 1.25 is not available. 1.2, 1.3 is there, but our in this problem it is 1.25. I have to interpolate it. In order to interpolate, I should check the boundary conditions here. 1, 2, 3, 4. You will find that all 4 edges are discontinuous. It is a single room. There is no extra room adjoining. Only one room is there, which is normally impractical, but usually this problem is there in the question paper. 4 edges discontinuous. Slab is not continuous over the supports on all 4 sides. Single room. So in case of single room, for 1.2, 0.0072, for 1.3 digits, but our value of Ly by Lx is 1.25, as I told you in the previous class also. So this is 1.25 corresponding to 1.25. I need to interpolate these two numbers. I should end up with a value which is in between these two. That is what is alpha x calculation. So alpha x is calculated like this. Now you can see here table 26, then Ly by Lx is 1.25. Directly it is not available. I have to see the case number 9. In the problem, totally 9 cases are there in table 26, which is the case for the given problem. Corresponding values of alpha x and alpha y should be calculated. In this problem, it is case 9. I'm going to give you one more problem in which case 9 is not there. Some other case is there. That also you have to, depends upon the boundary conditions, you should go there. So like this, I'm able to interpolate the two numbers. See this for 1.2, this is the value of alpha x. For 1.3, this is the value of alpha x. For 1.25, what is the value of alpha x? So it is 0.076. After interpolation, you have to do that one for case number 9. then alpha y is equal to 0.05. It is fixed. It is fixed for any ratios of Ly by Lx. Table number 26 is easy to find alpha y because you can see this. Alpha y is the last column. Last column. So it is not difficult to find alpha y because it is fixed. What he says here is for all values of Ly by Lx, let it be 1, 1.1, 1.2, any values of Ly by Lx, this value is fixed 0.056. So I'm going to choose, I'm going to interpolate for alpha x, for alpha y it is direct, no interpolation is required. Next you can see here, after this, alpha x and alpha y both are calculated. Now after finding MUX and MUY, higher value is 17.33. Now you compare this value with MU limit. So MU limit is 0.138 FCK BD square. You should remember B will be 1000 in slabs. So 1000 is fixed for slabs. D is 145. I have calculated MU limit 58.03, and highest of the two, higher of these two is 17.33. It means MU limit is more than MUX as well as MUY, which means it is under reinforced section, depth is enough, depth is sufficient. So two conclusions are drawn here. One is depth is adequate and the section is under reinforced. See, two conclusions will be there because MU limit is more than MUX or MUY. It is more than that. So reinforcement is calculated using different formula here. I already told you number of formula 3, 4 are there. Out of that, the fastest is SP16 table 2. So from this one, I'm able to find out that I'm able to calculate AST X and AST Y. When you calculate AST X, observe this. Use this formula, or I told you to use SP16. If anybody is not knowing, I'll explain it some other time. How to use SP16 table 2 to find out AST value. Fastest method. So 349.4, we got it as ASTX. ASTY, how to calculate here? Formula will be same. Here, when you calculate mu, use MUY. MUY is different, MUX is different. So in the direction of 5 meter, I'm going to find out AST. In the direction of 5 meters. So I'm going to find the steel here. ASTX means it is in the direction of X. Along this line, ASTX, which is related to MUX. Along you need to be careful here. Along this line, 5 meter line, it is ASTY. It is related to MUY. These green lines are MUX. Using MUX, whatever AST you calculate, that is green lines. Using MUY, when you calculate the AST, that is ASTY, we call it as, that is these red lines. Like this, both are main reinforcement only. So ASTX is 349.4, ASTY is 264.1. It must be checked. Both these values should be more than AST minimum. One more condition you should remember here is, whatever values of ASTX and ASTY we have calculated, they should be more than AST minimum. Otherwise, you have to provide whichever is more out of these three. Out of ASTX, ASTY, AST minimum, whichever is highest value, corresponding to that value of AST, steel should be provided. But in this case, what has happened is ASTX is 264.1, which is more than the minimum value. Even ASTX, this is ASTY actually, ASTX is also more than 2041. That is why we are not going to use this one. This will be used in edge strip. I'll tell you where it is used. I'm going to tell you where this minimum steel is used later on. Now both ASTX and ASTY are more than AST minimum. So you fix the bars. either 8 or 10 mm. Let us use 8 mm bars. Spacing of short span steel. Spacing of short span steel. I'll draw this figure once again. Let us say this is, now when I say spacing of short span steel, I mean these bars. These are 8 mm. I need to find the spacing now. See, all of you mute your this one. Mute it. Using 8 mm bars, spacing of short span steel is 1000. See, all of you check your mic. Mute it. Mute it. 8 mm bar, how to find the spacings? That is 1000 area of one bar into total area ASTX. Okay, 1000 is the width of the slab. One B is equal to 1000. So B is 1000 taken in slabs. 1000 into area of one bar divided by ASTX. This is ASTX. So I end up with 143.8. As per IS code book, the condition is the spacing should not be more than this value, or 3D, 3 into 145 or 300. So out of these three values, the smallest should be considered. Smallest is 143, that is rounded off to a smaller number 140. See, whenever spacing is 143, something like this, you should not go to 145. 145 is a round number. It's not like that. The bar should be as close as possible. It means either you keep 143.8 exactly, or if you want to round it off, go to 140, not 145. What will happen if you choose 145 means area available will be less than 349. You are reducing the area if the space is increased. So the bar should be as close as possible. As close as possible means if you cannot provide 143.8, you keep round number 140, but don't go for higher values because you are spacing them more. If the spacing is more than 143.8, say 150 or 145, the area reduces. 349 will not be there now. That is why round it off to a smaller number in case of spacings. So out of these three, smallest is 143.8. I am going to round it off to 140. So this is the steel in the direction of X. Next is similarly you go with ASTY calculation. 264.1, it is ASTY was calculated. 1000 into area of one bar divided by this. This spacing will be more because area is less here. So 190.2 or 3D or 300. Smallest is again 190. What I have done, 190.2 is rounded off to a smaller number, which is 190. 8 mm at 190 center to center. In this way, the bars are provided. If you see the diagram here, along the x-axis, the spacing is, how much is that spacing? 140. Because MUX is more. Along the y-axis, the spacing is 190. Bar diameter is same, but spacing is different. The spacing is more 190 because MUY is less than MUX. That is why MUX bending moment is more, spacing is, they are closely spaced. Here they are not so closely spaced. It is 190, it is 140. The simple reason is MUY is less than MUX. So again you can see this. So this is this is the end of your design means you know the diameter, you know the spacing, everything is done. So 70% of the design is over. Now, how to position the reinforcement, which is very important. Now you are having, let us say, how to draw this figure. I will explain now. You are having two values. One is along y direction, 8 mm, 190 center to center, 8 mm, 140 center to center along x-axis. You are having only these two. How to provide this one? How to draw this figure? I'll show you. I'll not show you the dimensions here. I'll just show you the position of reinforcement. So you draw this figure like this. Now carefully observe this one, how the reinforcement is provided. First I will provide I am having only 8 mm at 190, 8 mm at 140 along x and along y directions. But here I have to do some arrangement. Before I do that, I have to divide this one into panels like this, panels. Ly by 8, Lx by 8. Observe this. Now I'll divide this short span into three panels. Just observe it. Before I provide the reinforcement, I'll divide this one into three panels. This is one line. This side. This is Lx. You can see this one. Already it is done. Lx by 8, Lx by 8. Same thing. But I am showing it separately. This is Lx by 8. Panels are three panels. This is Lx by 8. You have to actually calculate and you can say that much is the dimension. Remaining 3/4 of 3/4 of series. 3/4 of Lx is remaining length. Total is Lx. It is divided into three panels. 3/4 of Lx. So this is, I am going to divide this one along short span. Similarly, what I will do, I am going to divide along the longer span. Again, I will draw these dotted lines like this. Ly by 8. This is Ly. You can, I am just telling you, Ly by 8. This is also Ly by 8. Whatever is left between is 3/4 of Ly. So the dimension of middle panel, whatever you are seeing right now, middle panel is 3/4 of Lx, 3/4 of Ly. Okay. The middle panel is, these are all edge strips. The middle strip is, this is middle strip. So what is the size of the middle strip? 3/4 of Lx, 3/4 of Ly. That is what is, we call it as a middle strip. All remaining portion is edge strip. It is strip is edge strip. All around it is edge strip. Now why it is required is, in the middle strip, the dimension of which is 3/4 of Lx and 3/4 of Ly. I am going to concentrate. I am going to provide the reinforcement, whatever I have calculated here, these two. So 8 mm diameter at 140, it will be concentrated only in the middle strip now. So I'll show you that one, how it is done, because it is separate class is required for this actually. So these are the bars which are 8 mm at 140 center to center. We need to extend them. I'll tell you later on. Some bars will be extended here, but basically, theoretically, I'm telling you, theoretically, what is happening, I'm telling. Theoretically, in the middle strip only, those reinforcements are concentrated. So 8 mm at 140 center to center is this bar. Now, 8 mm at 190. 8 mm at 190. You can see this. So in the middle strip only, I am going to provide. These are all 8 mm at 190. So mainly my requirement is because bending moment is maximum only in this middle strip. And when you reach the ends, what happens to the bending moment? Near the support, what is happening? It is zero. So this much of steel is not required in the edge strip. That is why it is economical. Here we have to provide only nominal reinforcement. In the edge strips, how to extend these bars up to the support, I'll tell you. Main diagram is different. Theoretically, I'm telling you, I need the bars only in this area because in the edge strips, bending moment is very less. No steel is required actually. So in both the directions, the bending takes place. That is why in both the directions, main reinforcement is provided. Now, what will happen to these edge strips? Whether bars are there or not, and what will happen to these main bars which are there in the whether they are extended or not? That question remains to be answered. Before that, what happens to the edge strips is you have to provide minimum steel in that. What is that minimum steel? AST minimum. Whichever is the most minimum I have to provide. These are the two bars here. These are the two bars which are of higher diameter, 10.5 at 300 center to center. In the edge strips, two bars are running like this, two bars are running like this. On all the four edge strips, 10 mm rods at 300 mm center to center. Hardly two bars are available. That much space is available now. So it means minimum steel is provided in the edge strip. How I got this one? 10.5 at 300 is using minimum steel formula. How much is that? 204. So in order to find the spacing in edge strips, what I should do? I should use this value. This is minimum of all the three. So using this value of AST for 10 mm, the spacing is 384.8. Observe this. 384. But spacing should not be, whenever minimum steel is used, 5D is taken, not 3D. It should not be less than whatever value 384.8 or 5D or 300. The smallest is 300 here. Smallest is 300, so 300 has to be kept for 10 mm diameter. What I have done here is in the edge strips, whatever edge strip is here, no, this surrounding, other than the middle strip, remaining all is edge strip. There I am able to provide only two bars. You can see two, all are overlapping there. At the corners they overlap. So these are the two bars of 10 mm diameter. Their spacing is 300 mm center to center. In this way, I have to calculate. It means in order to draw this figure, you need three AST values: ASTX, ASTY, and AST minimum values. Using three values only, I am able to draw this steel reinforcement detailing accurately. Now, what I have done here is, you can see the horizontal main bars along X direction. It has gone into one bar enters this side, left edge strip. You see this how it is continued here. It stops at the middle strip, the other end. Next bar, it goes uh, it goes to the edge strip of other end. See these bars, they are of same length. They are of same length, but one bar is there in this edge strip. The next bar is there in this edge strip. Again, you see the next bar, it is there in this edge strip, but whereas it has not entered the edge strip of the other end. So each of these bars, they are entering in one edge strip, but at the middle strip only they end. Since the length is same, just you go on placing it like this. One bar will place in this way. The bar bender will be doing this. So he'll place the bar same length, both are same length. He'll place this bar like this. Next bar he's going to place like this. So the second, if you see this bar, it has entered this alternately. What I'm trying to say, alternate bars are there in edge strips. There is no bar which is only present in the middle strip. No such bar is found. Either it has entered one of the edge strips. It has to enter. In this way, the final diagram is drawn. Theoretically, this is okay. Another 2 bars in all the edge strips is okay. But practically I have to do like this. Same thing happens for vertical along y direction bars. Alternately, they are extended. Then you can see the mill strip. First bar is, let us say, this one. It has entered the edge strip there. Next bar, actually it should come this side. It should go to the edge strip of this side. Again that side, again this side. It should run like that. I'll send the actual diagram. I'll share the actual diagram but in the examination, this much is enough. If you draw this much, it is enough. You're asked to draw the plan here. This is enough. I am showing ASTX here, ASTY and AST minimum. How they are placed, I have shown in the diagram. LX by 8. This diagram is there in the code book. Huh? This diagram LY by 8, LX by 8 is there in the code book. If you want, I will show it here. It is there on page number 90. Page number 90. So that is LY they have taken. I have taken LX in this way. LY this way I have taken, but everything is same. LY by 8, 3/4 of LX. This side also 3/4 of LY and all that. Middle strip and edge strips. So this diagram will be there in the code book only. So this is how the design is done, but still it is not over because I need to check it. When you calculate ASTY, D will be, see this, be careful about D value here. D will be less. It will not be 145, it is 137. See, whenever you calculate ASTY, D will not be 145. You have to subtract one diameter of the main parts. That is what I have done here. So D is 137 when you calculate ASTY. D is different because I have already told you because of this diagram. Okay, these are the main bars along X direction. Circles are main bars along Y direction. So for the bars which are running along Y direction, this D should be taken. So subtract 8. So 145 minus 8 should be taken. So 137. This figure makes everything clear. See this. This hatched bar is there. No, it is X direction bar for ASTX. D is 145. Circles are for, they are running perpendicular. They are running along the longer direction, 5-meter direction. So this is effective depth of circles. So it is this much is D now. Total is 145 minus 8 mm. 8 mm, it will be 137. So when you calculate ASTY, D should not be 145, it should be 137. You have to be careful about this. Rest all is same, everything is same now. Diagram I have explained. Next is this I will not explain this one. Check for shear. Simply calculate TOSI into BD. And compare this one with WU LX by 2. WU LX by 2. Always TOSI BD will be more in case of slabs. No question of any stirrups. So don't waste too much of time for shear in slabs. You have to use minimum time to say that stirrups are not required because TOSI BD is more than VU. So no question of wasting your time here. But check for deflection, you have to follow it properly. Same formula. LEX by D allowable should be more than or equal to LEX by D actual. LEX by D actual is direct. 4150 is LEX divided by 145 is small d. 28.6. So allowable should be more than this. Whatever value you calculate, so LEX by D basic into KC, KT, KF. No KC, no KF will be there in slabs because it is not a doubly reinforced. There is no flange here. Slab design it is. Slab design. So KT has to be calculated. So LEX by D for simply supported beam or slab is 20. 20 into 1 into 1 into KT. KT is calculated using PT and FS values. So I think you just go back and try to understand this. Already this has been explained. Finally, KT I got it as 1.56. KT is 1.56. I'll substitute 20 into 1 into 1.56. I'm getting 31.2. So 31.2 is more than actual whatever is happening. Actual what is happening 28.6. So permissible is up to 31.2 I can permit, whereas actually it is 28.6. So permissible value is more than whatever is actually happening. So the deflection criteria is satisfied. Criteria of deflection is satisfied. So all of you once again go back, try to follow this method. In one of the video lectures, it is explained how to find out. Again and again, I'm telling you here how to find out this one using IS code. You have to learn this one. It will be there in beams, it will be there in slabs. Procedure is same. This is directly 4150 by 145. Direct it is. This requires this all calculations. LHS requires all these calculations. You have to refer the table, you have to refer the graph. Graph is there. Go finally 31.2. So how I got LHS 31.2? If you know it, can easily understand. Means you know deflection check proper. So how I got 31.2? You should understand carefully because RHS is straight substitution is there. So this is the end of your slab design. I'll stop it here now. See, two-way slab is over. Two-way slabs with corners free to lift. Table 27 I have not solved. That is very easy actually. I'll give the notes of that. But in the meanwhile, I'm going to start continuous slab. In the meanwhile, you study this two-way slab with torsion. Torsion I think I have not covered it. No? I have to cover that one. This problem is not yet over actually. I think I have not taken those pages. In tomorrow's class, I think torsional steel, I think I have not explained this. If it is not there, I will just continue in the next class because that is also important here. One step is not there in this. Time is also over. So in the next class, I will explain one more step of this problem only. I will not start continuous lab now because torsional steel has to be explained. As you can see here, see this. Step 3 reinforcement is given. Check for shear I have explained.